Hello everyone. Today's lesson was not intended to be a video lesson, but I'm home with my sick daughter, so I'm going to go ahead and do a video on this one. Hopefully we'll be able to get that done. Tomorrow in class we'll talk a little bit about some of the implications of what we're going to do today and some of the application. It may move our quiz back a day. Things might get a little bit tight before winter break, but we'll see what we can do. So today we're going to discuss exponential growth and decay. And you see the picture here. For a lot of you, this is going to be something interesting because we're going to talk a lot about money, and we're going to talk about how to invest money and how money grows when you start talking about exponential growth and percent change. So this is going to be something that will hopefully be interesting to a lot of you. Today I'm going to give you a lot of formulas and things to help you calculate it. Tomorrow I'll answer a lot of your real world questions and we'll have a discussion on money. So here we go. Hopefully this makes sense. So as I said, we are going to talk a lot about percent change and compound interest. We're going to talk about how things grow in relation to a percent changing them. So there's going to be 4 formulas we're going to use today, and so we're going to go through 4 different examples. This video might get a little bit long, but you'll get a lot of time to work today with the substitute being there. So there are four variables we're going to start with here that you need to understand. The first one is going to be A. A is the amount of money that you will have after the interest is added. So in other words, after you do the calculation, how much money do you have? That's going to be the answer to most of our problems. P is the principal investment. So that's the original amount of money invested, or if we're talking about percent change, you may be looking at a situation like population growth, where P might be the original population and A would be the amount that remains of people after the percent change. So this is going to talk a lot about money, but understand in some cases there are questions that are going to ask non-money questions as well. R is going to be our rate, which is going to be your percent, but remember, we never plug percent into a formula the way it looks. We're always going to change that percent into a decimal. And finally, T is going to be the time that you leave that money in an account, or the time that it's been that a population would be growing. So, all right, let's look at our first formula. Our first formula is going to be for annual growth. Annual growth is going to be used when you look at anything changing over time, especially things like population, and that's going to be an example you see a lot. So you see the formula. A equals P times 1 plus R to the T. And the reason why we do that 1 plus R, that rate is going to be a decimal of growth. And we add 1 to that because when the population grows, or when an account grows, you get to keep that original amount plus that percent increase. That's what the 1 does. The 1, when you multiply by 1, it stays the same. So you get to keep that original amount. All right, let's look at this example. The population of a small town is growing at a rate of 2.3% per year. The current population is 3,850 people. How many people will live in the town in 20 years if that growth rate continues? What we're looking at is in some ways an advanced concept, but what we're going to do is going to be just simple plug into a formula and do calculations. So if we want to calculate this solution, we take in order to calculate our A, we take the original P, the original population or the principal amount, 3,850, times 1 plus the rate. You notice the rate here, 0.023. 2.3%, you move the decimal 2 places to make it into 0.023, and our time is T, 20 years. So you plug 20 in for T. The nice thing is this can be plugged directly into your calculator exactly the way it looks. If you plug in 3,850 parenthesis 1 plus 0.023 parenthesis to the 20th power, it will take care of order of operations, and you will find that there will be 6,067 people living in the town after those 20 years. Understanding you are always going to round to a number that makes sense. If we're talking about people, we will always round to a whole person. right, let's look at our second formula. Our second formula is going to be relative to annual decay. So we're talking about losing value. Decay means to break down or to lose. So you notice the formula looks very similar. A equals P times 1 minus R to the T. The small change being that now we're going to subtract that rate. So therefore we're going to lose value because we're going to be multiplying by a number less than 1. Our example, your new car loses an average of 11% of its value each year. It was purchased for $31,500. How much is it worth after 6 years? Again, we're just going to plug directly into the formula to come up with our solution. A is what we're looking for, the amount the car will be worth after 6 years. We plug in the original amount the car was worth, $31,500, times 1 minus 0.11 to the 6th power. Again, from here, it's just calculator math. If you understand the formula, you'll be able to simply plug in and let your calculator tell you the answer, that the car is now worth $15,654.91. Again, we have the rounding question, and the rounding question should answer itself. We're talking about money. When you round with money, you're going to round to 2 decimal places because we're talking about dollars and cents. All right, let's move on to our third method, or our third formula for calculating compound interest. This third model, compound interest, is going to be a realistic model for how many things are calculated in the real world today. Normally, when you invest money in an account, you're going to get paid interest. Maybe monthly, you'll get a bank statement where they'll pay you interest. It may be quarterly, which would mean you get every 3 months you get it because you get paid 4 times a year. So this is the idea that they're going to pay you interest more than once a year. And the nice thing about compound interest is the more often it compounds, the more money you're going to get paid. Because every time they pay you interest, that money goes into your account. Then, when they go to calculate the next month's interest, you already have now that previous month's interest added in. So you have more money in the account, which means you're going to get a higher payment the second month than you did the first. So you see our formula here. It has a new variable in it. There's an n in this. An n simply means the number of times it's going to compound in 1 year. So if it's monthly, n would be 12. If it's quarterly, n would be 4. Daily, n would be 365. So let's look at an example of this. In this problem, we have a young man who's investing his graduation money, and he's decided he's going to save that money for retirement. He's going to start young and think about the big picture. So in this case, you see, he invested $12,000 in an account that is going to pay 3.6% interest, and it's going to compound monthly. The question asking, how much will be there if he wants to retire in 40 years? So in order to do that, we have to plug into our formula. In this case, it's going to compound monthly, so our end value is going to be 12. So our solution, where we are trying to find A, is calculated by taking 12,000 times 1 plus 0.036 divided by 12 to the 12 times 40 power. In order to do that, this one is not quite as nice for plugging into your calculator. A lot of people make mistakes with this one. So the trick to getting this one correct with your calculator is to do the multiplication of the exponent first. Do the 12 times 40, which is 480. And if you do that first, you can then plug the problem exactly the way it looks into your calculator. 12,000 parenthesis 1 plus 0.036 divided by 12, close the parenthesis, to the 480th power. If you do that, you will get $50,539.29. I strongly suggest you do that and practice it right now. Make sure you get that answer. If you're not, ask someone around you so you guys make sure you're plugging these into your calculator correctly. Alright, our fourth and final formula is going to involve something that is compounding continuously. That means your interest is being paid to you constantly. It's not waiting for a day, a month, even a second to start paying you more interest. It is constantly paying you more and more interest. So to do this, we're first going to have to introduce a new number, and that's the number e. It's e because it's named after a mathematician from Switzerland named Euler, and so it's called Euler's number. E approximates to 2.718, but much like other numbers such as pi, it is an irrational number that goes on forever. We just round it to around 2.718. You will find a button on your calculator that says e to the x power. That's the button we're going to use here to represent Euler's number. That number comes from what we call the natural base of the natural logarithm. We're not going to get into those this year, but we'll discuss that more in pre-calculus. For what we need to know for this class, we have a formula that we call the PERT equation because it is A equals P times e to the RT. All those variables are the same, and remember, e is not a variable. E is a constant value. It's just a button in the calculator. Alright, so let's look at our example here. In this example, you invested $1,350 in an account, paying 6% interest, compounding continuously, and we're going to leave that money in there for 15 years. So again, you see the solution at the bottom of the page. It looks exactly the same as the formula. We've just replaced P, R, and T with their values. When you look at the solution, $3,320.46, again, that's just a calculation from your calculator. You can plug that in and it will give you the answer directly. So like I said at the beginning, we'll discuss this more tomorrow on how banking works and how some money things work. I'm sure you have a lot of questions. For today, we're just going to get in the practice of plugging into the formulas and coming up with the solutions. All right, we'll see you tomorrow.